Okay, so good morning, everyone. Let's start our CERC group meeting. Today, Julia Marcucci will talk about machine learning by nonlinear waves, a new road for neuromorphic computing. So thank you, Julia. As it is your first time talking here to the CERC group meeting, I would like you to introduce yourself and talk about your background. And that's it. Thank you very much.
Thank you. Thank you, Daniel. And thank you all for being here attending this talk. So I'm a very new postdoctoral fellow in the group of Bob here. And my background is strongly mathematics, I can say. So I have 2 degrees, one in mathematics and one in physics. And so in my PhD thesis, I applied many mathematical methods to the study of nonlinear waves, especially in current media and nonlinear non-local media, and also disordered media. And the last part of my PhD was about the study of optical architectures to realize machine learning. So I can say that I studied machine learning from 2 different points of view, and this is what I'm going to show to you today. So one point of view is just related to the algorithms that machine learning is offering to the physics community. And so I studied, I don't know, so for example, TensorFlows and other codes that we can use to do machine learning. And from another point of view, I studied the way to realize optical neural networks or artificial neural networks that perform machine learning to optics. And this is, I think, that it wasn't published. So I got my PhD in February, and then I started a long process to come here. But this paper wasn't published when I got my PhD, when I defended my thesis, but was published a couple of months ago. And so no, maybe just 1 month ago. And it's kind of the summary, I can say, of all the work that I have done in the last 3 or 4 years. So I'm very happy to be here to present this work. So essentially, this work deals with the way to realize an artificial intelligent machine by light propagation in nonlinear media. So let me start from a very simple question, even if it's a very fundamental question. What really is artificial intelligence? Is that a hardware, is that a software? So if we consider how movies from the late 90s describe the artificial intelligence, we think of a sort of awakening of the consciousness of machines that makes the machines able to do very complex operation, up to thinking autonomously, and also to I don't know, to start a revolution, to raise up, and even to feel affection. But artificial intelligence nowadays is something very far away from this, and it's essentially a supercomputer. So a machine that is able to do very complex operations at very high speed. So like the Fugaku supercomputer in Japan, that would be the fastest supercomputer in the world from next year. But artificial intelligence is not just that. Artificial intelligence could be also an optical setup. Like, for example, the spatial photonic Ising machines, even that we realized 1 year ago in my previous university, that is essentially just a spatial light modulator, so a very simple setup, a spatial light modulator, and free space propagation of light, and then a CCD camera and a loop, a feedback loop between the CCD camera and the spatial light modulator. And through this, we were able to solve a very complex problem, that is the minimization of spin glass Hamiltonians. Artificial intelligence could be also a way to realize machine learning. So if, for example, we consider this our paper that we published a couple of months ago, where we have the same setup I showed you before, but with a biological sample between the spatial light modulator and the CCD camera, we can see that we can perform a specific architecture of machine learning, that is the reservoir computing, in which the biological medium acts like a reservoir, and it's able to disclose by itself if it presents cancer, if it doesn't, and at the same time, if this cancer is growing and how fast it is growing. Artificial intelligence could be also the way to realize deep learning, that is maybe the most famous machine learning architecture, by a nanophotonic circuit, as what was done by Soljacic's group in MIT. So they realized this deep learning architecture in which they were able to do vowels recognition just by a cascade of controllable Mach-Zehnder interferometers. So artificial intelligence, I can say, to summarize, that nowadays is machine learning. So it's the way to make a machine learn. And the way we can make a machine learn is by considering an artificial neural network. So an artificial neural network is like the one reported here. It has at least always 3 layers. The input layer, one hidden layer, but we can have many, many hidden layers, as in the example I showed you before about deep learning, and one output layer. And the output layer is just a nonlinear function activation, function computed on a superposition of the nodes of the last hidden layer superimposed to a bias term. And please keep in mind that the activation function must be nonlinear, because without nonlinearity, we cannot make the network compute non-trivial problems using only a finite number of nodes. So I'm talking now about artificial neural networks. So it seems that machine learning now is an algorithm, when before I showed many hardware systems and many photonic systems. So is machine learning an hardware or a software? The answer is that it could be both. So it could be an hardware when we consider, for example, the nanophotonic circuit I showed to you before. It could be a software when we want to solve through machine learning codes complex physics problem, or it could also be both, as demonstrated in this paper, where we realize multi-level quantum gates through machine learning using a TensorFlow programming language. And we show that the same thing could be done by using a feedback loop for a multimodal fiber propagation, for light propagation in a multimodal fiber or in a random medium. So this is what I'm going to show you today. I'm going to talk about machine learning, but not as a software, as a new hardware. So I'm going to show you a new hardware design that is able to do very complex operations using just optical nonlinear wave propagation. And I will show you that this new hardware is able to interpolate, to classify, and to realize logic gates. So this is the outline of my talk. I will show you why we got interested in this topic, and it's essentially to disclose the inner link between nonlinear waves and science of complexity. So to demonstrates that nonlinear waves are able to solve very complex problems. And I will show you what we did. So what kind of machine learning architecture we realized. So I will explain how neuromorphic computing works and how it is able to emulate the human brain. I will show you how we did that. And it was by using a wave reservoir that takes advantage of the propagation of a paradigmatic system that is the nonlinear box after being structured by a spatial dye modulator. And then I will show you the final goal of this paper here, that is the realization of our architecture called the single wave layer feed-forward network. So let me start by disclosing the link between science of complexity and nonlinear waves. So science of complexity is a very broad field. I can say that it's more a class of fields. So it was developed in at the very beginning of 40s when people started to study systems theory, cybernetics, and also artificial intelligence. And then nowadays it's a sort of a container of many fields of science, including also nonlinear physics. And if we consider the literature about science of complexity, this literature is very vast. But when we think about the most famous books about science of complexity, they all agree on the same point, and it's that science of complexity is placed at the edge of chaos. What does it mean? It means that science of complexity studies systems that are neither ordered, like crystals or light-free space propagation, nor disordered, like particle gases or light scattering, but they are in the middle of the two. They are half order and half disorder, like, for example, soliton gases and filamentations. And our approach consists in finding a complex system that is able to learn and compute in order to demonstrate that complexity solves complex problems. So we choose a peculiar complex system that is the one related to optical nonlinear waves. So first of all, let me show you that optical nonlinear waves are complex. Indeed, if we consider this paper written by Alex Gaeta and Bob and others, where they studied the polarization in the output from isotropic medium of two counter-propagating light fields, they show that if we are in a linear regime, so if the total transmitted intensity is low enough, we have just a periodic signal, so essentially an order signal. But if instead we increase the total transmitted intensity, we can see that we reach a chaotic regime. So we are at the edge of chaos in this case, because we are moving from an order system to a chaotic system. The same happens when we consider this paper by Conti about the filamentation in nonlinear non-local disorder medium. So we have media. So we have a medium which has a noise, a disorder, and the nonlinearity is a thermononlinearity. And we generate filaments in this medium. And we can see that when the degree of nonlinearity is low enough, these filaments are just interacting at the very beginning of their propagation, but they are not interacting anymore along the propagation. If instead we increase the non-locality of this medium, we can see that we move from a disorder regime to an order regime, so to a regime that is half order and half disorder, because we have the emergence of these clusters of filaments while enhancing the non-locality. And the same happens when we consider the energy landscape of light propagating in an optical fiber. And we can see that this energy landscape in the phase space is a complex energy landscape with many minima. And the absolute minima gives us the emergence of rock solitons, but essentially the high amount of minima makes this energy landscape as complex as the one of a glass. So we established that linear waves are complex, but linear waves are also controllable. As we can see from this paper published last year, I will not go into details about this, but essentially we realized that we can control the output from a photorefractive crystal by controlling the value of topological invariance at the end of the propagation in our crystal. So linear waves are also controllable. So they are complex, they are controllable. Can we do computation by nonlinear waves? Yes. And this is what I'm going to show you today. And this is a very important point because it means that complexity explains complexity by itself. And not only that, but also that complexity explains complexity at the speed of light. How? By mimicking the most complex system we have in the world, the human brain. So let me tell you how we can mimic the human brain. So through this complex architecture that is called neuromorphic computing. So the human brain is the most complex system in the world because it is a network of complex adaptive systems. Complex adaptive systems are essentially the protagonists of the science of complexity, and they were studied at the beginning by Murray Gell-Mann from the Santa Fe Institute in the 80s, but right now their concepts are applied to all the fields of science of complexity. And essentially, they are systems in which the whole is greater than the sum of its parts. So systems in which the dynamics is able to change the interaction between the single agents. So we are no more able to describe the system just thinking about the agents and their interactions. And every task that the human brain is able to accomplish is a complex adaptive system like the language learning and others. So the neuromorphic computing is the machine learning architectures that is able to emulate the human brain and to solve problems related to these complex adaptive systems. And it's essentially a brain-inspired computing for machine intelligence. I read here, it promises to realize artificial intelligence by reducing the energy requirements for computing platforms. And this means that it really emulates our brain, because if we think about how many complex operations we can do by our brain just with a spoon of sugar in a cup of coffee, we are really reducing the energy requirement for computation. So since it is an architecture in the machine learning scenario, I will, I talked before about machine learning and deep learning, and I showed you that in deep learning we have many layers, but we can have access to every layer and to the weights of the connection between the nodes in every layer, as it happens when we consider, for example, the paper by MIT. But when we consider instead neuromorphic computing, this is no more possible. We have a reservoir between the input and the output layer, and this reservoir acts like a black box. So is a box that we cannot have access to that. We cannot know how the nodes of the reservoir of the network are connected between each other. And so it means that when we consider an artificial neural network, we have, instead of the hidden layer, this reservoir. And the way to realize the reservoir by optics is by substituting to the hidden layers light propagation. And this is what we've done. And we realized this reservoir computing neural network in which we have an input layer, a wave reservoir, and an output layer. But the wave reservoir must be a complex adaptive system. So it must be a system in which the propagation is able to change the nature of the nonlinear waves along the propagation itself. And to do this, we consider a paradigmatic system that is the box problem, and I will explain now the box problem in the next slides. But the most important feature of the box problem is that it is able to show all the most important characters in the nonlinear wave world. So it is able to show dispersive shock waves, or I can say waves that resembles dispersive shock waves at the very beginning of its propagation. So waves that experience wave breaking during the propagation. And for this reason, the intensity is all focused on the borders, and then they develop these very rapid oscillations called on-your bores. Or we can also see that we can have, talking of nonlinear waves, ROG waves. So very intense peak that immediately appear and suddenly disappear from a flat background. And we can also have shape invariant propagating waves called solitons. So this is these are the main characters in the box nonlinear propagation world, and I will show you this model now here. So this model was studied by L and co-workers in this paper of 2016, where they started from a nonlinear Schrödinger equation with an initial condition that is a box-shaped beam. So essentially, you have light propagation in a Kerr medium, and so a medium in which the intensity varies with which the nonlinearity varies with the intensity in a focusing way, and the initial condition is a CW laser beam with a shape that is a rectangular shape. And you see that at the very beginning you have diffraction by edges, and this diffraction by edges gives us patterns that are very similar to the one of the dispersive shock waves. And then you have at a certain propagation length the generation of ROG waves in the analytical form of peregrine solitons and Akhmediev breathers. And the long-term propagation is a soliton gas. So here we have more or less all the protagonists of the nonlinear wave world. And this is how we created our wave reservoir. So by the propagation of this box-shaped beam in a Kerr medium. And this way we created our single wave layer feed-forward network. So a network which has, of course, an input layer, a reservoir, and a readout, and of course also an output layer. And the input layer is made through an encoder which is able to map the input in a superposition of plane waves with either different phases or different amplitudes. And this superposition, it depends on how you do the encoding. So you can do an encoding in phase, or you can do an encoding in amplitudes. I will show you later. And this superposition of plane waves is superimposed to our box-shaped beam, to our rectangular beam. And this represents now the input of our nonlinear crystal or whatever, so our nonlinear medium. So we let this input propagate into this nonlinear medium that is a Kerr medium rule, where the propagation is ruled by the nonlinear Schrödinger equation. And then we detect the output after a propagation length L. The output is detected by a CCD camera. On the CCD camera, we divide the pixels in clusters, and we average the value of the intensity on every cluster. And then we superimpose this value by these weights, beta here, and we get our output. So to tell you how we can realize this in a laboratory, we need, at least for the simplest setup, we need a CW laser and a CW laser that impinges on a spatial light modulator. The spatial light modulator acts as the encoder. So it gives to our beam the different phases or the different amplitudes that store the information on our input along the propagation. And we need also a lens because we need to consider the far field. So in the far field, we have this superposition of plane waves, and this superposition of plane waves is superimposed to another CW laser beam. This CW laser beam is a box-shaped beam, and then everything goes on into a nonlinear crystal or a nonlinear medium in general, so a Kerr isotropic medium. And then we detect everything through a CCD camera. We divide our pixels in clusters that represent our channels, and our channels are weighted to get the output. So this is an example of one of the problems we solved through this single wave layer feed-forward network. And we solved here the interpolation of a sinc function. So the results shows the training points, so the theoretical points of the sinc function in the red circles, while the blue dots show the values computed by our network after the training. So as you can see, an exact reproduction of the of our sinc function. And the way to do this is to consider a training set that is our y values along the y-axis, that here I call t because it's related to the fact that these are training points, but these are the y here of our problems. And to every x, I can associate, of course, a training point, so a y value. All the x's are encoding, so are represented as a string of binary numbers through this way. And we decided to have strings with a length of 12 points. So this nx here is equal to 12. So this way we get for every point of the training set, so for every training point, we get a string of digits 0 and 1, and to every digit 0, 1, we associate a phase 0 or pi. So we transform our string of digits in a string of phases on our SLM, and then we consider, as I told you before, the far field. So this point here is this point here in which we have the superposition of plane waves that have the information on our input encoded in the superposition. Then we need a bias term, and for us, our bias term. So essentially, since we are talking about nonlinear propagation, the bias terms is the one that switch on the nonlinearity in our system, and for us is a box function. Then we let our input given by the superposition of the box and the plane waves we let our input propagate into the Kerr medium, and we detect everything by our CCD camera, and so we get the intensity values of our channels. So for every training point, we get an array of intensity values. Then we repeat this procedure for every training point, and so we place our arrays into a matrix H, that is the matrix of our output. And that is the matrix, no, sorry, of our channels, so of the values of our last layer. And our output is then given by H times beta. So where beta is the vector of weights that we use to superimpose the channels at the end of the CCD camera to get our output. So our output for the entire training set, so all the function for us is given by H times beta. And of course, we can say that the network is able to learn when this H times beta is very close to our training set. So when we have the superposition between the red circles and the blue dots. And when we find this beta that is able to give us these results, it means that the network learned, and from that point on, we are able to reproduce our function without considering the training set anymore. So, of course, we have an exact learning condition when this limit is inequalities. So here I want to show you our results related to this. This is just the propagation of the box into a Kerr medium, and this is the propagation of the box when we consider the superposition with the plane waves. So these are plots made at high nonlinearity, and this high nonlinearity, but with this high nonlinearity, we can see that we have anyway two different behaviors. The first behavior is in which the number of channels is much lower than the number of training points, and for the reason we are not able to interpolate the function, when instead the number of channels is equal or even higher than the number of training points, we have a perfect interpolation of our function. So we have two different learning transition. The first learning transition is related to the number of channels. So we need to have a number of channels that is high enough. And the second learning transition is related to the nonlinearity. So we have a nonlinearity threshold that expresses the fact that we need a high complexity for making our network learn. And this is the summary of what I've just told you. So the two fundamental conditions, the number of channels that must be at least equal to the number of training points, and the high nonlinearity. And when we have this, we can say that the network is able to learn, but we need complexity to realize these results. This is another example that we realized related to realized through this single wave layer feed-forward network. So we consider a very famous data set in machine learning community, that is the Abalone data set. So it's a data set that gives for every Abalone here 8 parameters, and through these 8 parameters it is able to say how old the abalone is. So we realized a network and we trained the network in order to get the normalized age of every abalone starting from these parameters. And you can see here that we have the same results we had before. So we have a learning transition depending on the number of channels, but also a learning transition depending on the amount of nonlinearity. And then let me also tell you that here the encoding was made in another way. So we used an encoding based on the amplitude. So instead of having a superposition of plane waves with different phases, here we have a superposition of plane waves with different amplitudes, and every amplitude is related to one of the 8 parameters of every abalone in the data set. And for this, we realized that the nonlinearity and also the propagation of the box in our medium depends on the way we do our encoding. Indeed, we need much more nonlinearity here, and we reach a regime in which our box is able to show also the emergence of log waves. And this is the last example you can find on our paper. That is the realization of logic gates. And also this realization of logic gates was made through a binary encoding, so an encoding in phase instead of in amplitude. We realize an AND gate through this. And if you want to take a look at the supplementary material, I think that these are this is interesting too, because we show that our system is quite stable also in presence of noise, and that at the same time I can say that I had a lot of fun in demonstrating this theorem, this representation theorem, in which we mathematically prove that when you have nonlinearity in your system, you can really make your network learn, but otherwise you can't. So it's mathematically proven. And let me briefly acknowledge the people, the two people who work with me on this paper. So my PhD supervisor Claudio Conti, and my colleague Davide Pierangeli from Sapienza University of Rome, an Institute for Complex System in the National Research Council of Italy. So here are the conclusions of my talk. I showed you that it is possible to find a complex system that is able to learn and to compute as a human brain, and that we can have this complex system and we can make it learning by considering linear wave propagation. So by considering linear wave propagation and realizing a neuromorphic computing architecture, we realize what we call the single wave layer feed-forward network. And through this, we show that a nonlinear wave reservoir enables learning, but only when we have complexity degrees high enough. So only when we have a nonlinearity that is high enough. And this single wave layer feed-forward network is also able to do a lot of complex operations like interpolation, classifications, and the logic gates. So through this, we can affirm that complex nonlinear waves can solve complex problems, but also that they can do that at the speed of light.